let's do this thing. So like I said, we're chapter 13 is really big, so we're gonna continue it today, chapter 13 part 2, but I'm also gonna sneak chapter 14 in there, which is just a little itty bitty guy. I know, rude. But most importantly, I guess, quiz number 3 on Tuesday. The weeks are just slipping through our fingers. It's just happening. So quiz 3, it's going to be on chapters 11 through 14. But 13 is pretty big. Morning. It'll just be the 50 minutes again. It's all chatty. It'll just be a 50-minute quiz again. Yeah. We can do it. First the quiz, and then we'll do some an Excel little thing blip. We'll have seen a lot of it already with the Excel commands that we're introducing for the Z-scores, right? Finding areas under the curve, which is what we'll continue with today. But before I start, any questions from last day? No. Okay, not yet. We introduced properties of the normal distribution, right? And so we talked about the normal distribution and how we'll be able to leverage it in a lot of different scenarios. And most importantly, the areas under the curve are probabilities, right? They're proportions and percentages because all those 3 P's mean the same thing. But the areas under the curve are probabilities, and that's an important aspect, right? Because that's how we'll be able to assign probabilities to things. We introduced Z, right? A standardized value, which follows. We also introduced, this is my way of reviewing the shorthand, right? Z follows a normal distribution with a mean of 0 and a standard deviation of 1, right? And so in general, right, we can say X follows a normal distribution with a mean mu and a standard deviation sigma, right? That's our shorthand. Right? Knowing that something follows a normal distribution, right, that's how we're going to be able to relatively easily find probabilities associated with outcomes. The simplest way to find those probabilities without Excel, right? In Excel or on your calculator, you can kind of do things relatively easily, and you can just plug in an X and a mu and a sigma, and it'll just calculate Z in the background, right? And then it'll integrate it and do all the work. But for us, one of the simplest ways is to first calculate a Z, right? So we worked on calculating Z scores, which is basically saying how far is X, so some observation X that I'm interested in, how far is X from the mean, right? Taking into account the spread, right? And we looked at the SAT scores and the ACT scores, and I did look it up, and now I can't remember quite, but I think the maximum SAT score was 1600, but we were pretending that there was an 1800. Makes me think that it was probably like an old score or something. I think it used to be out of 2100, but anyways, an unlikely score. That doesn't matter. So Z is going to be useful both for finding probabilities, but also for determining the width of our confidence interval, right? We're building up towards confidence intervals as well, okay? And so Z is going to help us find the critical value for our confidence intervals, right? How many standard deviations do I need to move out to capture the central 95%? Well, then we introduce the 68, 95, 99.7 rule, which is a quick kind of rule of thumb that we can use to approximate areas, which are also probabilities, right? And so what it says is roughly one standard deviation we can move out. We've captured the central 68% of the curve. If we move out 2 standard deviations, then we've captured the central 95% of the curve. And that's why in a confidence interval, often you'll have seen in the past, and I'm talking about Sydney's class, you probably saw something like this, x bar plus minus roughly 2, probably 2.143 or something silly like that, but basically 2, right? Times your S over root n. Generically, we call it T star, that 2. Okay? But that 2, basically 2, comes from the 68, 95, 99.7 rule. And so we're going to build up to that. But I know you've seen it already, sort of. Well, you've seen it. You've done it. Now you know sort of why. So we can use this rule, just quick guide to approximate areas which are probabilities, and that's pretty useful, right? No calculator required. Although I did play around with our calculator, or I guess mine's old. Mine's the old version of your calculator. But the first one, that first option that's in there, if you go to your stats menu that we found last day, I have a normal PD, and I had to talk to Susan about it. I was like, I don't know, what is this thing doing? What the normal PD is doing is if we give it a Z, it gives the Y value, and that's really stupid. We don't care about that. And so I'm going to erase that, but that's all it's doing. So basically just ignore that normal PD. I have a normal PD option. Do you guys have a normal PD option there? Yeah, just ignore it. We want the CD, the cumulative distribution, right, up to and including that point. And today we'll also introduce the inverse normal, where is it? Inverse normal option, which if you had to guess, what's that going to do? It's going to take some area. So, right, the normal CD function, it takes a Z and it gives you the probability, and then the inverse is going to take some probability and give you a Z, right? Moving back and forth between those two, right? Which is how we find, okay, what value do I need to use for a 95% confidence interval here, okay, for example. But let's do an example as review. Okay. I decided we're done with the SAT scores and the ACT scores. The max is 1600, but I feel like the old one may have been 2100 or something, because 1800 is tough. You're going to get in everywhere, though. It's a knockoff SAT score. Let's talk about heights. So based on a sample of 100 men, the heights of adults who identify as male between the ages of 20 and 62, why 62? I don't know, in the US is nearly normal, with a mean of 70 inches and a standard deviation of 3.3 inches. We're working in inches, that's okay. Cameron is 5'7", 67 inches, and Adrian is 6'4", which is 76 inches. What's Cameron's height percentile? Remember, a percentile is, right, the percentage below. We'll focus on Cameron's height, and then we'll do Adrian's height, because they'll behave the same way. First thing you're going to do, if you see that something is nearly normal, you can start off by drawing that curve. That's a good place to start. Mine always ends there, but close that up. If it's nearly normal, I have to give you the mean and the standard deviation, right? And so then I give you the mean, which is going to be the center. And the standard deviation is 3.3. Usually I just jot down the standard deviation somewhere below it. You could take the time to add 3.3, add 3.3, add 3.3, and just kind of have some markers, but we don't need to do that. And so, but you could, if you really wanted to, right, kind of map out the 68, 95, 99.7 rule, right, with 3 standard deviations in either direction, but we don't need that yet. Okay, so we want to find, okay, so Cameron is 67 inches. That's slightly below average, right? We want to know, okay, well, how much below average, right? And so what we're going to do is put 67. This is a number line of the heights, right? And if the average height is 70 inches, then we understand that most men are going to be around 70 inches, right? There are people who are shorter and people who are taller, right? But they happen less frequently. So if I put 67 inches here on this number line, really what I'm looking for the percentile is I want to find, okay, this area. And usually I shade it in and I put a little question mark there to indicate to myself that that's the thing that I'm looking for. So I want to find what percentage of heights are below 67 inches. How do we do that? We can standardize it, right? We can find our Z, or if you play around with your calculator, right? Because it'll just take the mean and the standard deviation. You could do that. I'll do it old school. So the next thing I need to do is I'll put a little subscript K on there for Cameron, because later I'll have Adrian, and so it makes sense to differentiate between the two. And Z is really just saying how many standard deviations away from the mean is this height, right? And then that is your Z. So x minus mu over sigma, and we could put a little xk on there if you want. "67 inches is 3 inches below 70, but the spread is 3.3. And no, I will not do that in my head. Oh, thanks, Stefan. I get negative 0.90909, blah, blah, blah. Let's round this, negative 0.9091. So that means that 67 inches, right? How do we read this? 67 inches is 0.9091 standard deviations below the mean, right? The negative just tells me that I'm on the lower side, right? Below the mean. It's close to 1, right? And so we've got some options for finding this area under the curve. Right, let's use the 689599.7 rule just to solidify that a little bit. Yeah. Let's wait. Using the 689599.7 rule, can draw this out. Now we can talk about Z. Z is centered on 0, right? We said Z follows a normal distribution, right? And so what we've done, all we've done really, is taken all these heights, right, and standardize them so that they're now on this standardized scale. And we found, and sigma is 1. We found that our score of 67, or our height of 67 inches, put us at a Z of negative 0.9091. That's somewhere between 0 and 1 standard deviation below the mean. And so what we can do is we can say, okay, well, here at negative 1, we decided we had how much in the tail. If I moved 1 standard deviation on either side, then I have 68%, right? Which means I have 32% left over, and I split that evenly amongst the tails, right? And so here, not a great estimate, because this thing, this negative 0.9091, right, is somewhere between 0 and 1 standard deviations below the mean, right? And so here at the mean, by symmetry, how much area will he have in one of the tails? Should have 0.5. That's a pretty shoddy estimate, right? We can do better. Bless you. And so, right, because it's saying, oh, the percentile is somewhere between 0.16 and 0.5. Right? That's good. That is an answer, right? And then we use software to find more accurate percentiles. We could use other tables like the t-table, for example, which will break it up, right? It just breaks up your interval into more breaks than just 1, 2, 3, right? But that's all it does. So here, this percentile so using the 689599.7 rule, we estimate the percentile to be between 0.16 and 0.50. I will add in brackets, not a very good estimate, right? Probably closer to 0.16 just because we know how close to -1 we are, right? with a Z of negative 0.9091. But that's really all we can say using the 689599.7 rule. So not very precise. Or we use software, which can include your calculator if you want. How about this? I'll do it in Excel. Oh, but it was misbehaving yesterday. Let's see here. Norm.s.dist. The S means it's standardized, and so if you play around with the norm commands, there's a norm.dist, which lets you plug in your mean and your standard deviation, and so you don't have to give it a Z, right? And so, but we're working with Zs right now. So let's see here. I'm going to use the rounded value, but if you're able to plug in the X and the mu and the sigma, it'll give you a slightly better value for Z, but it shouldn't make a huge difference. And this is where, wow, I don't want those brackets. There. This gives us the area to the left, right? Which happens to be the area that we want. Is that somewhere between 0.16 and 0.5? It is, right? And so our estimate was, reasonable, but it just wasn't very precise. Bring it in. Oh. Cancel. Your upper is going to be the 67, but your lower, you can make it like negative 99 or something, because it needs to know what the bounds are. And so if you want kind of everything to negative infinity, it won't take infinity, obviously, but it'll kind of take 99, something large. This is from last day, so we can ignore that. But here, right, and find the area to the left is 0.181649, right? Which means that the percentile is for Cameron is 18.165. I'm not very good at rounding. As in, I can't help it. I hate to do rounding. Therefore, Cameron is at the 18.2th percentile. Remembering that percentiles are the percentage below. I'm just gonna bump that down. So from software, we found that this was 0.181649. Now, I don't want to assume that you know how to work your calculator in the quiz, And so what I'm thinking I should do is just give you kind of Excel output, right? And then just kind of put it all together on the front page, like in the formula sheet, like we had. And then you can grab the information that you need. Okay? And so, but you'll need to know kind of what to look for. Okay? For example, it would say something like this. Norm.s.dist for negative 0.909 with cumulative equals true is equal to 0.181649 is how it would read on the front page, along with other things, and then you can grab the things that you need. Okay? So it's part of it, or you can just use your calculator. Right? You find the same thing on your calculator. You can try it.
So you're saying like you would start with the question and get that first bit and then look at the front and figure out which one.
Yeah,
okay.
Exactly. Yeah, because I don't want to assume that you can work your calculator under pressure. That's rude. Yeah. Right. So and a calculator that does it is not required, and so that's why I feel like I'll just give you the information that you need. But if I give it to you in the question, then there's no question left, right? And so I know, but do that. No. Okay, so that's my solution. Okay, so we found Cameron's percentile. What's Adrian's percentile? You can find Adrian's percentile, right? Do the same thing, but 76 inches. Okay. What do we already know about 76 inches? Well, it's above the mean. And so already I'm expecting my percentile to be more than 50%, right? Once I cross the mean, then it's more than 50%. Bless you. Yeah. And so it's good to kind of check in. Same with the 67, right? We expect it to be less than 50%, right? Because it's on the lower side of the mean. So let's do Adrian. Adrian is 76 inches. Adrian's percentile at 76 inches. They're being pulled from the same distribution, right? A normal distribution of heights centered on 70 with a standard deviation of 3.3 inches. Then we do the same thing. Where you put that mark doesn't really matter, as long as you're on the correct side of the mean, right? It's just to help you visualize things, right? And so I put nearly no effort into where I'm gonna put this little thing. So here I'm gonna put 76 because I want to give myself just enough room on either side of 76 that I can do other things, right? So it's just to help you visualize. So here, what we're looking for, and just so I'm not shading like crazy, I'm looking for this area, right? The percentile for 76 inches is all the area below 76. So to get there, what do we need to do? We need to standardize this thing. And so Z for Adrian, I know it's going to be positive, right? Because it's above the mean. And so I can take X for Adrian minus the mean over sigma. And I get 76 minus 70 divided by 3.3. I get 1.81818. Repeating. Let's round that just so I don't have to lug that around. 1.8. How many did I round to before? 4. Just to be consistent. 4 is usually safe. What this means is that Adrian is 1.8182 standard deviations above the mean. Right? Quite tall. Right? Almost 2 standard deviations above the mean. Okay? And so let's see here. We'll approximate it with the 68, 95, 99.7 rule. Right? 1.8182 is between 1 and 2. Right? Kind of boils it down a little bit. So first, use the 68, 95, 99.7 rule to approximate the percentile. Remembering that the percentile is the area below, so we need to do a little bit more work in terms of our 68, 95, 99.7 rule. But here I have Z, which is centered on 0 with a standard deviation of 1. I found that we are 1.8182 standard deviations above the mean. What I want is this area. So I close this off, right? Between 1 and 2, again, it's just to visualize. In fact, maybe I'll bump that over here, even though that's not, technically correct. But I need room to write all these. We did some work last day to find areas using the 68, 95, 99.7 rule, right? And so if you had to figure out what's the area below a standard deviation of 1, well, down to -1, we have a total area of 68%. But then I also have the tail, right? And so it's going to be 0.68 plus 0.16. 0.68 plus 0.16 is 0.84. I need more space. I really cramped my own style. 0.84. So that's going to be the area to the left of a Z of 1, or anything 1 standard deviation above the mean. We can do the same thing for 2. Now I gave myself tons of room for 2. 2 standard deviations, right? 68, 95. So now I have 95 with 5% left over, split evenly amongst the tails. So now I have 97.5, right? And so I have 0.95 plus 0.025 is 0.975. This is a better estimate for the percentile, right, than the one previously. It was quite wide. Now It's still not great though. It's between 0.84 and 0.975, right? And so we can do a little bit better, right? But how did I phrase it before? We estimate the percentile to be between 0.84 and 0.975. Or we can use software. And I encourage you to try it on your calculator, but I'll use Excel because I don't have a fancy calculator on my screen. Or using Excel, we find, I wonder if I can just change this. I can. Sneaky. 1.8182. I think 0.965483. Come on. So again, you can ignore the rest. Especially this dot, it's in a cell. It's weird. But is 0.965483 between 0.84 and 0.975? Sure is, right? And so we are able to approximate it, but of course, software makes it better. 0.965483, which I'll put here, 0.965483. Which means that Adrian is at the 96.5th percentile. Maybe this doesn't need to be quite so big. Therefore, Adrian is at the 96.5th percentile for heights. You can do the same thing for test scores, right? And I think I mentioned there are kind of professional exams where you have to be at the 95th percentile in order to pass. So that depends on how the rest of the group did, right? It's not a score. You have to be at the 95th percentile, which means 95% of people scored less than you, right? You just need to do better than everyone else. Yeah. And so, right. And if someone tells you, oh yeah, my baby's at the 90th percentile for weight, they've got a chunky baby. Or if they're in the 10th percentile, they're a little tiny baby. Often, I hear people bragging about being in the 10th percentile for the test scores. What do they actually mean? They mean the 90th percentile, right? They mean the top 10%, right? But what they're actually saying is only 10% of people scored less than them. That's not really that great, right? And so I know what they mean, but they're not saying what they mean. So what else could we do? We could figure out, okay, what proportion, let's use some not new terminology, but kind of fresh terminology in this sense, right? Because we've talked about percentages and probabilities, and proportions are all the same thing, right? And so now a follow-up question. But I was so quick. A follow-up question. Could be what percentage, or sorry, what proportion, I said I was going to use new terminology. What proportion of males between the ages of 20 and 62, right, are between these two heights, right, are between Cameron and Adrian's heights? What proportion of males between the ages of 20 and 62 are between Cameron and Adrian's heights? Okay, let's have a look back. Proportions are probabilities, are percentages. Really what we're looking for are areas under the curve. Right? And so we know the total area under the curve is 1. We've already used that to find our puzzle pieces, right? And so we can take it one step further, and we can say, okay, well, I know heights are nearly normal, centered on 70 with a standard deviation of 3.3. And we had 67, I think it was. 67 and 76. We already found those areas, right? In fact, we use software to find the exact areas. We found that this area was 0.18 something. Copy. Paste. And we found that this area was this. Copy. Paste. So if I know those two areas, right, but the area that I want, right, so what proportion, that tells me I'm looking for an area that satisfies this criteria. They have to be between Cameron and Adrian's heights. And so here's Cameron, here's Adrian. So I'm looking for this area here. Kind of sloppy. That area, right? There are lots of different ways that we could find this value, right? But I think the easiest way, as long as you treat them like puzzle pieces, you could do weird stuff, but the easiest way, I think, is to take, okay, well, what if I have this whole piece, and then I just lob off the piece I don't want, right? That works. We're allowed to do that. They're just areas, right? And so if you just think of them as pieces that have to add to 1, right, then you're safe. So 0.965483 minus 0.181649. Who knows? .181649. Unless I did something weird, I get 0.783834. You could approximate it with the 6895 99.7 rule, but it's a hot mess. Why? What would you have to do? You'd have bounds on this little guy, and you'd have bounds on this little guy that we found. And then you're gonna have outer bounds right here, and then you're gonna have inner bounds here. And it's still not a very good estimate. I'm gonna remove all that because we don't need to do that. Okay? You could do it, but why? Dink, dink, dink. Clean this back up. Okay? So therefore, the proportion of males between Cameron, K, and A's heights, get lazy here, is 0.783834. Which means that roughly 78% of males are between those two heights. Okay. We need to be really comfortable with finding areas under the curve, right? Because those are going to be our p-values, right? And so, let me add that here. We need to be comfortable finding areas under the curve since they will be our p-values. We've already seen p-values. Okay. So everything that we talk about, or a lot of things, I should say a lot of things, not everything, some exceptions, follow a normal distribution or a nearly normal distribution. And so that's how we're going to be able to attach probabilities to some point estimate that we've seen. Okay. And so in general, what we're going to find, right, I'll do HT hypothesis testing. Have I defined that yet? I feel like I have, but I should do it fresh today. In hypothesis testing, we did, but it's been a while. So in hypothesis testing, we want to assign probabilities to some point estimate. We will want to find probabilities associated with a point estimate, which is generic on purpose. Yeah. But what's nice is one of the ways that we can do that, or we can analyze a point estimate, is we can say that Z is going to be your point estimate, right? That's your best guess from your sample, minus the hypothesized value right? How far is this thing from where you think it should be or might be off of? And we'll obviously build this out more, but I want you to see that the z's are going to come back. Okay? And then instead of the standard deviation, this has the same form so far as x minus mu, right? How far is the x that we've seen from the mean, right? And instead of the dividing by sigma, we're going to divide by the standard error of the point estimate. So that point estimate is going to have some spread, which is going to take the place of sigma. And so there's kind of mathematical models that establish, okay, if you have a point estimate, such as a p hat, then the math for finding the standard error of that point estimate is the square root of p hat q hat over n, for example, p naught q naught. We'll save that for next week. But we will get to a z because it will follow a normal distribution, assuming some conditions have been met. Okay. So we need to be comfortable finding areas under the curve, okay, because that's going to help us find our p-values. Then in confidence intervals, right, we need to figure out, okay, if I want to build a 90% confidence interval, right, then how many standard deviations or later standard errors will I need to move out to capture the central 90%? Okay, and so in those scenarios, we need to be able to work backwards is how I think of it. Okay? Because then I have an area under the curve and I want to find what Z makes that happen. We will also, Yusuf can wait. We will also need to be able to find, can I call them critical values or just Z scores? Let's do both. Find Z scores, which we'll call critical values, for different confidence intervals. For different confidence intervals. Because a confidence interval generically looks like this. You have a point estimate. Hey, that sounds the same as earlier. I know, right? So I have my best guess from my sample, right? My p hat, for example, right? And then I go down a little, up a little, right? In order to capture the central 95 or 90 or whatever, 99% of the curve, right? And so here, this the Z star indicates that it's a critical value. That changes to a T star later, but the critical value aspect stays the same. And so the critical value, this determines how many, not sigmas anymore, right? But how many standard errors we need to move out to get that confidence level that we want. Determines how many standard errors we need to move away from the point estimate for a desired confidence level. So our confidence interval is going to be our point estimate plus minus our critical value times the standard error of the point estimate. Right, so that point estimate is going to have some spread, right? Kind of taking the place of sigma. Right? So for example, I feel like we already did it, but I can't remember exactly. Example, find Z star for a 95% confidence interval. Right? We know it's 2-ish, right? But we're going to use 1.96 because it's just slightly more accurate. Find Z star for a 95% confidence interval. I'll define CI confidence interval, but I know I did that last week. So really, what we want is we want to force 95%, right? The central 95%. How many standard errors will I need to move out? Well, if I work on the standard scale, right, of Z, then Z is centered on 0 with a standard deviation of 1. So now I can find, okay, if I have, I know I'm expecting this to be roughly -2, and I'm expecting this to be roughly 2. Right? We know that from the 68, 95, 99.7 rule. But let's see if we can find what it actually is. Okay. If I'm forcing 95% in the center, I have 5% left over in the tails, right? Which I have to split evenly. And so I have, 0.025. It wants it as a proportion, right? And so 2.5% is 0.025, which means, and the reason I'm doing the area to the left is because most software will just take the area to the left, right? We can always do kind of take the total area of 1 and subtract it, right? And so this becomes 0.975, right? You've got the central 95 plus the 0.025, puts you at 0.975, right, to the left. But we also know that this should be 0.025, and we know that these two need to add to 1. Right? So we've got lots of tricks up our sleeves. Now I'm curious, this is going to use the inverse of the normal. And so to find the corresponding Z scores, we need to use the inverse normal. Oh yeah, I was gonna try it on here. My inverse normal, it wants the area. Now that's gonna be the area to the left, right? And so if I do it on my calculator, 0.025, and it defaults to a Z, which has a standard deviation of 1 and a mean of 0. So let's go ahead and click through, and I get negative 1.959964028. I'll do it in Excel as well. Let's see if I can do. Can I do it? Equals norm dot s dot inverse. Same thing. If you don't want to use the standardized, the Z value, then you can just go norm dot inverse. But for confidence intervals, we always want the Z, right? So norm dot s dot inverse, and it just needs the probability, which I'm going to force it to be 0.025. Oops, 0.925, 0.025. Nice. By symmetry, I expect it to be the positive version for 0.975. Let's try that. 0.975. Positive version. Youssef passed away. I've been moving him down this whole time. So it wants the area to the left, right? But then it returns the Z that makes that happen. And so we find that, let's see here, 1.9599964, and let's do Z equals, and Z equals negative 1.9599964. Or in general, for a 95% confidence interval, it's okay if you use 2, but I would prefer it if you use 1.96 just for cleanliness. So for a 95% confidence interval, we will use Z star equal to 1.96. I'll put in brackets here. Slightly more precise than 2. Spelled precise. Back in my day, we had to memorize all these critical values, right? 90, 95, 99, 98% confidence intervals, etc. Rude. We don't have to do that. But 1.96 is easy enough. Okay. So we can also use this scale. So this is how we're going to use, I think of it as working backwards, right? Because in my mind, working forwards is I have a Z and I find the area, right? Now I have an area and I need to work backwards to find the Z that makes that happen. Okay? So if someone tells you, oh yeah, I scored in the 10th percentile on that test, you need to be able to figure out what the score was, right? What their score was. It's bad. Or here Yusuf, I've been bumping him down this whole time. Yusuf's height is at the 40th percentile. How tall are they? So for this, I'm not going to bother with the 68, 95, 99.7 rule, right? Because we get a poor approximation. Just going to jump straight into using software for this one. It's more for quick approximations for probabilities that I use the 68, 95, 99.7 rule, which is also called the empirical rule for if you're Googling. But I like to call it exactly what it does. All right. First thing you're going to do is draw this distribution, right? So annoying. What if I don't need to draw it? Then how will I know how you interpreted the question? Right? Because as long as you follow through and what you drew may not make sense with the question, but as long as you followed through with what you said you were going to do, that's worth a lot of marks, right? And so if you can show me, okay, when I read this question, this is how I interpret this, right? Then I can kind of follow along, right? So I encourage you to draw the picture. Draw the picture. Well, it looks like this. Heights are still centered at 70, and they still have a standard deviation of 3.3. If Yusuf's height is at the 40th percentile, that means 40% of heights are below his height. Okay? What does that tell me about where he falls on this number line? I know for sure he's going to be below the mean, right? Because at the mean, that's the 50th percentile, right? And so he has to be somewhere below the mean. Okay? And so let's draw that. I'm going to try to find this height, right? So then I put a little question mark there saying, okay, that's what I'm looking for. And I'm going to force this area to be 0.40. Okay. We're going to be able to find the Z that makes this happen, right? And then we can work it backwards and kind of unravel it to become an actual height. And so we first find how many standard deviations Yusuf is below the mean. That's really a long way of saying we need a Z. Right. Okay. If I have a probability and I want a Z, I can use the inverse, right? That's an inverse function. And I'm just going to change this little guy here, hey, to be 0.4. Can ignore. So it would say something like equals -0.25. I didn't do it for the previous one, but hopefully you get the idea. And you just need to know, okay, which one am I looking for? And then you can grab that number that you need. This tells me what? Tells me that Yusuf is 0.25335 standard deviations below the mean, right? Because it's negative, right? You want to keep that negative, right? Because otherwise you'll be above the mean. And so this is our Z is negative 0.25335. If Z is x minus mu over sigma, now we're trying to solve for this x. Right? Now I have a Z, negative 0.25335. Right now I'm just trying to unravel this, okay, knowing that he's 2.5335 standard deviations below the mean. Well, that means I can multiply it by 3.3 to find the standard deviations, right? And then add it to the mean. So I get x minus 70 divided by 3.3. This just becomes an exercise in algebra, right? Multiply by 3.3 and then add 70. I'll do it nice and slow. Negative 0.25335 times 3.3 is x minus 70. Let's figure out what that is. Wait, wrong. Negative 0.25335 times 3.3. Negative 0.83605 is x minus 70. And so x is negative 0.836055 plus 70. Right? Adding 70 over and then doing a switcheroo. Which means he's 69.163945 inches tall. So at 69.1 inches, let's say, or 69, then you're at the 40th percentile. Pretty nice. Not looking sold. Did I write something weird?
Seems weird that 70 is that.
Yeah, like the 40 percentile, but you're like less than an inch difference.
But the standard deviation is only 3.3. Right. And he's only a quarter standard deviation below the mean. Weird. Okay. Good. How much time do I have? Oh no. Okay. Okay, fine. I do want to talk about decision errors because it's chapter 14, but it is just a little tiny blip. So just to give you a sneak preview, it's a little blip. The central limit theorem, which is just as important as it sounds, says, among other things, that p hat follows a normal distribution centered on the population proportion P with a standard error of P Q over N. Q is 1 minus P. It's just my shorthand for 1 minus P, because I get lazy. Keeners. They're not in this class, they're just hanging out. Really throwing me off. Must have a test or something. So here, I use this shorthand of Q, but it's really just 1 minus P. And so the square root of PQ over N, that dun, 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 is the standard. Hey, that was a bad dun, dun. Hey, I want a beautiful, okay, better. This is the standard error of P hat. P hat is a point estimate for P. Oh no. This is our point estimate. Wait, that's sounding so familiar from how we find our Z scores and how we find our confidence intervals. I know, right? But you have to wait until next week. Point estimate for P. Our best guess at what the population proportion looks like is P hat. And then we have this central limit theorem. Anything that's a theorem means that we can just use it and trust that it's true. Now, it is subject to some conditions. And so we can only assume it follows a normal distribution if some conditions are met. So this part here, we can assume it follows a normal distribution if some conditions are met. What are they? No, we have to wait until next week. Okay, fine. Your observations have to be independent of each other. And how can we accomplish that? Usually by randomly sampling, right? And so that's one way to be able to assume that all our observations are independent, but also I need to have a large enough sample size, right? And there are kind of mathy ways that we can check that, but I need a sample size that's big enough to pick up on the proportion that I'm trying to pick up on, right? Imagine just kind of intuitively, if you're trying to detect something really, really rare, right? A rare disease, for example, you don't want to just collect a sample of 50 and call it a day. Oh, I didn't see any, so it must not be happening, right? It's not really how it works, right? We understand that, okay, I'm going to need a big sample in order to detect a small p, and so that's what we're going to be dealing with. Yeah.
Is that a bracket between N and P?
Yes. So it's using that notation where x follows a normal distribution with a mean mu and a standard deviation sigma. It's just shorthand.
So it's not square rooted.
It's the this takes the p is the mu, and the square root of pq over n takes the place of the sigma. So it has a different spread, right? It's just a measure of spread. More on that next week. But for now, I want to do, wait, where is it? Chapter 14. Like I said, just a little blip. And she's got lots more examples, but I think it would take me 2 weeks to get through all of them. Because I blab a lot. Decision errors, chapter 14, refers to, I was doing so good. I was doing 1 chapter a day and it was totally reasonable. And then she threw chapter 13 in there. Oh, in 1 chapter? Are you kidding me? Decision errors refers to hypothesis testing. Okay. In hypothesis testing, right, we use the p-value and we compare it to an alpha level. We compare the p-value to an alpha level, right? And if it's less than the alpha level, usually 0.05, then we reject H naught. Okay. To the alpha level. Now, I think that was like Tuesday last week that we talked about the alpha level. So it's been a long time, but usually alpha is 0.05. You can adjust that, and we'll talk about why you would, but for now, usually your alpha level is going to be 0.05. Our conclusion is based off of if the p-value, whether the p-value is less than the alpha level or not, right? If the p-value is less than the alpha level, we say we have enough evidence to reject H naught. We have enough evidence to reject H naught. And if you're rejecting it, we can say in favor of HA. But for now, let's just say, okay, then I'm going to reject H naught. But as we saw in that randomization section, there were times where it just, that result happened by random chance alone, even when the null hypothesis was true because we forced it to be true, right? We randomly assigned the genders to the promotions, and we did find that some of them, right, were more extreme than what we had seen in our sample. So it is possible, right? But just as a rule, right, we say, okay, if the p-value is less than, and usually the thing is we have to pick an alpha level before we look at our data, right? Otherwise, it's so tempting to adjust our alpha level a little bit, right? And so you have a pre-decided alpha level. What does that alpha level mean? That alpha level is you declaring, I'm okay with being potentially wrong and rejecting H naught 5% of the time, right? And so this alpha level, bless you, the alpha level should be determined before the study. Should be determined, see, before the study is completed, right? Any data collected, anything like that. Okay. And the alpha level is kind of a threshold where you're okay, I understand that it could have happened just by random chance alone, but it's unlikely. And so then I'm going to reject H naught. And so the alpha level is a level where we would be comfortable rejecting H naught even if we shouldn't, okay, when H naught is true, and is a level at which we are, can I say okay with making a mistake or making an error or a decision error. There are two decision errors that we could make. There's a type 1 error and a type 2 error, and they are different. Usually we have kind of a, fine, I'll do the whole thing. Why not? Since I'm there, usually we set it up in a table like this. Yeah. Our population, right? There can be some truth, right? In our population, either the null hypothesis is true or the alternative hypothesis is true, right? And so this is kind of referring to our population. And then our test conclusion, right? I can reject the null hypothesis. If I reject the null hypothesis when the null hypothesis is true, that's a mistake, right? And so, right, if the null hypothesis is true, it means I should keep it. I shouldn't reject it, right? And so then if I reject it, right, because it just happened by random chance alone, right, just like we saw in those randomizations, then I'm making a type 1 error. You know? So rejecting H naught when H naught is true is called a type 1 error. Okay. If you fail to reject the null hypothesis and the null hypothesis is true, then that's a good decision. You made the right choice, right? The problem is we don't know if we've made the right or wrong choice, right? And so we need to attach probabilities to making, usually we attach probabilities to making a type 1 error, right? And that is the alpha level, right? So the alpha level is kind of a preset level where I'm okay making a type 1 error. Okay? Type 2 errors are trickier. Okay? They happen if the alternative hypothesis is true. Okay? So you should have rejected H naught, but you didn't. The type 2 error is harder to control. Usually we just control it by increasing our sample size, right? Our sample size wasn't big enough to detect that the alternative hypothesis was true, right? Because our spread was too wide, right? So usually we're concerned with the type 1 error. Okay? Notice that if you reject H naught, right, then the only kind of error that you could make is a type 1 error, right? And if you fail to reject H naught, then the only kind of error that you could make is a type 2 error. Right? And so there's always a chance that we're wrong and we don't know, right? And so the alpha level, is the probability of making a type 1 error. So if you want to reduce the probability of making a type 1 error, what would you do? You would make it harder to reject H naught by decreasing your alpha level, right? You need a way smaller p-value, right? And so to decrease the probability of making a type 1 error, we can decrease the alpha level. We can decrease the alpha level. Let's say it doesn't really work in terms of statistics, but if the null hypothesis, or if rejecting the null hypothesis when you shouldn't have is expensive, right? So let's say, rejecting the null hypothesis means that you're gonna apply some change. Let's say that change is you buy brand new machines for your whole lab, right? I don't know what statistic you would measure to come to that conclusion, right? But let's say it's monetarily expensive, right? Then if the null hypothesis, so if the truth is that you don't really need to replace all your machines, right, then you want to make it really, really hard to reject the null hypothesis, right? And so that's kind of monetarily expensive. But if we're looking at, vaccines and things like that, you want to be really, really sure that people aren't dying from it before you put it to market, right? And so, right, things like that. And so it can be expensive in different ways. And so to control the type 1 error rate, you can adjust your alpha level. Right. The type 2 error is kind of the little brother. There's not a lot that we can do to adjust for a type 2 error, right? That's if I fail to reject the null hypothesis when in fact it should have been rejected, right? There's not, a lot that we can do there, right? But if I fail to reject the null hypothesis, there's a chance that it should have been rejected, and that would be a mistake, right? A decision error. Okay? And so usually to adjust for a type 2 error, all we can usually do is increase our sample size. And so to decrease the probability of a type 2 error, we usually need to increase our sample size. We usually need to increase our sample size. Increasing our sample size is going to decrease our standard error, right? Decrease our variability. And so, for example, the standard error of p hat that we saw earlier, the square root of pq over n, right? What happens as you increase your sample size? Oops, do proper arrow. As you increase your sample size, not really knowing anything about this, but mathematically, if you increase the thing that you're dividing by, you're going to get a smaller number overall, right? So then the chain reaction is that this is going to get decreased, and all of this, once you take the square root of a smaller number, is also going to decrease. Guess I should use different colors. The standard error is the spread. Right? And so by increasing our sample size, we decrease our spread, right? We get more precise estimates. By increasing n, we decrease the standard error. Which is the spread. Which means we get more precise estimates, point estimates. Which means we get more precise, precise point estimates. And from more precise point estimates, we can feel more comfortable with failing to reject the null hypothesis if that's actually the case, right? If the null hypothesis is true, right? You don't want to be failing to reject it, right? Just because you didn't have enough evidence, right? And that's why we use that phrasing, right? You have enough evidence to reject H naught, that kind of thing. Okay. Nice. So, leading us. Yep, I can do it. From type 1 errors. And there are different scenarios, right? And so the court system is another go-to example again, right? And so if the person is innocent is true, right, then rejecting the null hypothesis is saying, hey, you're guilty, right? That's a type 1 error. That's a mistake if they're actually innocent. If they're innocent and you say they're innocent, then that's fine. That's a good decision. If the alternative hypothesis is true, that's the same as, okay, if they're guilty and they know they are, right? Then if you give them a guilty verdict, that's a good decision, right? Whereas if you say, oh no, you're innocent when they're actually guilty, that's a type 2 error, right? And so you can attach those to different scenarios. Yeah. But like I said, those court ones never really made sense to me until recent years. So it doesn't make sense, it's okay. But just remember, if you reject the null hypothesis, the kind of error that you could be making is a type 1 error. Whereas if you fail to reject the null hypothesis, the kind of error that you could be making is a type 2 error. Now, from the alpha level and the type 1 error, we saw a one-sided hypothesis test last week, right? Where we had the promotions and we suspected that fewer females were being promoted than males, right? But in saying that fewer, right, we're kind of applying some bias, right? And so that's what we call a one-sided hypothesis test. And so from last week, we suspected fewer females or a lower proportion of females, but let's say fewer females. No, be proper. A lower proportion of females were promoted than males. So when we set up our null and alternative hypotheses, right, we had this idea, right, a lower proportion, right, and we analyzed the differences in the proportions, and right, but this introduces bias, right? Bias from our perspective, right? I suspect that this is happening. It's also what I saw in my data, right? But in order to kind of, I guess, combat that, what we say is, well, what if we consider both sides, right? So not just if a lower proportion of females get promoted, we would also be concerned if a lower proportion of males were promoted, right? And so we would be equally concerned if a lower proportion of males were promoted. Which we can rephrase as, okay, is there a difference in the proportions? And so now, right, what we want to analyze if there's a difference in the promotions. If there is a difference in promotions. That difference in terms of our normal distribution. I know. You thought you were done with it. No way. If we're talking about the difference in proportions, and I know different from 0. Right. We can have the proportion of females minus the proportion of males. If they're the same, it's centered on 0, right? If more males are being promoted than females, then we would be down here. If more females are being promoted than males, then we would be up here. This is what we call a two-sided test, right? Because I'm concerned about both sides, right? And so here, we call this a two-sided test. Because we're concerned about both extremes, right? And it just makes it harder to reject H naught, because what happens is we find the p-value in one of the tails, and then we say, well, I would be just as concerned if that happened on the other end, right? So then we multiply it by 2, typically. Excel has a command for it, but it's okay. You can just multiply by 2. And so to find a two-sided p-value, we find the p-value like we usually would, and then we multiply by 2. Find the p-value as we usually would. Then multiply it by 2. I'll say to replicate it in the other tail. If the p-value has to be less than the alpha level, right, then multiplying my p-value by 2 makes it harder to reject H naught. A two-sided test has the added benefit of making it more difficult to make a type 1 error. Making it more difficult to make a type 1 error. Step away from the plate. There. And that's all on your quiz on Tuesday. Well, textbook questions, so no curveballs. If you have any questions, let me know. Otherwise, enjoy your weekend. See you on Tuesday. Thanks.